Hello everyone, this is Mr. M from Algebra Lessons. In this video, I'm explaining what is the characteristic roots and vectors of a square matrix. So before I'm going further into the deeper sides of the said topic, I would like to explain some basic information regarding this. The check marks are characteristic matrix, characteristic polynomial, characteristic equation, and characteristic roots or eigenvalues. What is characteristic matrix? So if we have a square matrix A, if we have a square matrix A, which is of order n by n. Suppose the order is n by n. And we are considering an indeterminate lambda. If I am choosing an indeterminate lambda, so then the matrix A minus lambda I. Okay, A is the parent matrix and lambda is the indeterminate, and I is the identity matrix of order n by n, because the parent matrix is having order n by n. So the matrix A minus lambda I will known as the characteristic matrix of the given parent matrix A. Say for example, if I'm having a matrix A is equal to 1 2 3 4 5 6 7 8 and 9. So the characteristic equation of this particular one or this particular matrix can be write as A minus lambda I is equal to matrix 1 2 3 4 5 6 7 8 9 minus lambda times I is the identity matrix of the same order 1 0 0 0 1 0 0 0 1. That is 1 2 3 4 5 6 7 8 9 minus each place of 1 we can replace it to lambda 0 0 0 lambda 0 0 0 lambda. Okay, so the final answer you can write as the final answer, or the characteristic matrix you can write as A minus lambda I equal to 1 minus lambda 2 3 4 5 minus lambda 6 and 7 8 9 minus lambda. Okay, see what is happening here. What is happening here is changing the main diagonal elements. This is the main diagonal element, so that main diagonal element is changing with respect to lambda. Okay. Okay, this is actually the characteristic matrix. And next we are going to explain what is a characteristic polynomial. Okay, how can we find the characteristic polynomial? Okay, we can use the same example. So here we have the characteristic matrix. So if we have a matrix of order 3 by 3 or n by n, whatever it may be, so I'm considering this same example for the whole explanation. So I have the matrix A that is 1 2 3 4 5 6 7 8 9, and we actually explained, or we found the characteristic matrix, and now we are going to find the characteristic polynomial. The characteristic polynomial of this given matrix A will be the determinant of the characteristic matrix. So the characteristic matrix of A is A minus lambda I, and the characteristic polynomial of A is determinant of A minus lambda I. That means determinant of let me try to write. So determinant of this matrix 1 minus lambda, 2, 3, 4, 5 minus lambda, 6, 7, 8, 9 minus lambda. Okay, so this is actually the characteristic polynomial. Okay, we need to expand and write this in the form of a polynomial. For that, you have to expand this determinant like this. Okay, this is equal to, just like the way you are explaining, expanding the determinant, you can do like this. Take the first row and expand on that row. So that will be 1 minus lambda times, so you have to hide the first column and the first row. The minor matrix is 5 minus lambda, 6, and 8, 9 minus lambda. So this will be 5 minus lambda, 6, and 8, 9 minus lambda. Okay, then minus 2 times the determinant is, you have to hide this column and this row. Remaining is 4, 6, 7, 9 minus lambda. Okay, then plus the last number is 3 times the minor matrix is, hide this column and this row, that is 4, 5 minus lambda, and 7 and 8. Okay, so expand it, that is 1 minus lambda times 5 minus lambda, 5 minus lambda times 9 minus lambda. Okay, minus, okay, you have to give this properly, the parenthesis, otherwise we'll make mistakes. So 1 minus lambda times 5 minus lambda into 9 minus lambda, that means the cross product, minus 8 times 6, 48. Okay, minus 2 times what is this, 4 times 9 minus lambda minus 42, plus 3 times 32 minus 7 times 5 minus lambda. Okay, you can simplify this. 1 minus lambda times 5 minus lambda times 9 minus lambda. So you can FOIL it. 5 times 9 is 45, minus 5 lambda minus 9 lambda plus lambda square. Okay, minus 48. Okay, minus 2 times 36 minus 4 lambda minus 42, this is minus 42, plus, okay, plus 3 times 32 minus 35 plus 7 lambda. Okay, so simplify it. So that will be 1 minus lambda times we have 45 minus 48, that is negative 3, and 5 lambda, 9 lambda, both are negative, so it is minus 14 lambda plus lambda square. That's the first term. And here we have 36 and 42, this is negative, so minus 6 times minus 2 is plus 12 plus 8 lambda. I hope you are following me. And plus 32 minus 35 is negative 3. Negative 3 times positive 3 is negative 9. And plus 3 times 7 is 21 lambda. So and expand this bracket to, this is -3 minus 14 lambda plus lambda square, and this is plus 3 lambda plus 14 lambda square minus lambda cube plus 12 plus 8 lambda minus 9 plus 21 lambda. Okay, we are in the final stage. Okay, go ahead and find the numbers first. -3, 12, -9, 12 plus -9 is +3, +3, and 12 got cancelled, so there is no number. Then we can go ahead with lambda. So 14 lambda, 3 lambda, that means -11 lambda, -11 lambda plus 21 lambda, that means 10 lambda. 10 lambda, so lambdas are gone. We missed a lambda here. Minus 14 lambda, so 11 minus 11 lambda minus 11 lambda minus 11 lambda plus 8 lambda means -3 lambda, -3 lambda plus 21 lambda is 18 lambda. This is not 10 lambda, this is 18 lambda. Okay, this is 18 lambda. Okay, we are done with lambdas, and we can go ahead with lambda square. Lambda square plus 14 lambda square is 15 lambda square, so that is plus 15 lambda square. So lambda square terms are actually done, and finally we have only lambda cube, so this is minus lambda cube. So this is the characteristic polynomial of the 3x3 matrix that we considered. Okay, now we need to find out the characteristic equation. What is the characteristic equation? So if we can equate this to 0, that means determinant of a minus lambda I, determinant of a minus lambda I is the characteristic polynomial. If we can equate this to 0, we can call it as the characteristic equation. Great. So what is the characteristic equation of this polynomial? This matrix A. So here we have the characteristic polynomial, and so equate this to 0, that is negative lambda cube plus 15 lambda square plus 18 lambda equal to 0. So we can rewrite this as lambda cube plus lambda cube minus 15 lambda square minus 18 lambda equal to 0. This is the characteristic equation of the matrix that we considered in the beginning. Okay, that was the 3x3 matrix. We actually define what is the characteristic matrix, then we define what is the characteristic polynomial, and now this is the characteristic equation. And finally, the last item that I mentioned there was characteristic roots or eigenvalues of the square matrix. So how can we find the eigenvalues of that square matrix? So basically, if you have the characteristic equation, you just solve that equation. That's what the basic idea behind the process of finding characteristic the eigenvalues. We have another method to find the eigenvalue of a square matrix, but if you have this characteristic equation, you can find the eigenvalues like this. Okay, we have a cubic equation, solve it. Fortunately, we have a cubic equation here with lambda on all terms. So just take the lambda out. Lambda times this is lambda square minus 15 lambda minus 18 equal to 0. So straight away you can use the product rule. So either lambda is equal to 0 or lambda square minus 15 lambda minus 18 equal to 0. So we already have one value for lambda is equal to 0 is the first eigenvalue of this this square matrix. Now we can try to solve this second degree equation just like a quadratic. We can try to solve using the sum and product. So the constant is 18. Solve it. Okay, what are the factors of 18? 1 and 18, 2 and 9, 3 and 6. Then that's it. So by using any pair, can you make the product 18 and sum, this is the sum and this is the product 18 and sum 15, but it should be negative. Okay, we can try. 1 times 18 is 18. 1 plus 18 is not 15. Even if we are changing the sign of any one of this term, it will not give you a 15. 2 times 19 is 18, but it is actually cannot produce a sum of negative 15. So the next one also is not generating that particular sum. So we can go ahead and find the solution using the formula. So we can write lambda is equal to the equation to find the value of or the roots of a quadratic equation by formula is x is equal to minus b plus or minus root of b square minus 4ac over 2a. Okay, we are actually going to plug this equation here. Okay, so lambda is equal to, this is the first term, so the coefficient of lambda is 1 here. This is the second term, coefficient of lambda here is negative 15, and here this is the constant. So we can write a is equal to 1, b is equal to negative 15, and c is equal to negative 18. We can try to calculate this. Okay, so this is the thing. So minus b minus 15 plus or minus root of b square, that is minus 15 square, minus 4 times a is 1 times c is negative 18 over 2 times a is 1. That is negative of negative is positive, that is 15 plus or minus root of negative 15 square or 15 square, both are 225. 225 negative times negative is positive, so this is 4 times 1 is 4, 4 times 18 is 72 over 2 times 1 is 2, that is okay, that is 15 plus or minus root of 225 plus 72, that is 7, 9 and 2. Yep, it is 297 over 2. So because 297 is a number that don't have any perfect square root, we can rewrite, or we can just split this into pieces and write as the answer 15 plus square root of 297 over 2 and 15 minus square root of 297 over 2. These are two values. So we are going to write our eigenvalues just like this. The eigenvalues of the given matrix with order 3 by 3 is lambda is equal to 0, 15 plus root 297 over 2 and 15 minus square root of 297 over 2. Okay, I hope this process of finding eigenvalues explains well and we actually need to get an idea of this kind of characteristic equation, or this kind of calculation, and we should have some kind of information, or we should have some kind of deeper knowledge of this characteristic roots and how it is behaving, just like using AB BA cases, because for matrix product AB is not equal to BA, but in the case of a characteristic root, if we have I personally think that I need to explain that also. That will give you a clear idea about the characteristic roots. So I just want to prove I have two matrices. I have two square matrices A and B, and I actually want to prove, we know that the product AB is not equal to BA. AB is not equal to BA. But what about the characteristic roots? The characteristic roots of AB and BA. We can check what is the characteristic roots of AB and BA. Will it be same, or will it be different? That's kind of an interesting question, or it is kind of giving you a deeper kind of thoughts about this characteristic equation. Okay, we know that if we have a matrix A, then the characteristic equation of A is determinant of A minus lambda I equal to 0. Okay, we are not considering a single matrix, we are considering the product of two matrices AB and BA. So if I have the product AB, that will be another matrix. That will be another matrix of the given order. Okay, so the characteristic equation of AB can be written as determinant of AB minus lambda I equal to 0. Okay, consider this as equation number 1. Okay. So now I'm actually assuming let lambda 1, lambda 2, lambda 3, etc. be the roots of the first characteristic equation. Okay, now multiply. We are actually trying to prove both AB and BA is having the same characteristic roots. Okay, so multiply equation number 1 left, on the left side, left by determinant of A inverse, and on the right, and on the right by determinant of A. Then what will happen? We can check that. What will happen? So the equation will be determinant of, let me try to use a different color. Okay, determinant of A inverse times AB minus lambda I times determinant of A. This is actually not making any difference because A inverse and A is there. Okay, so that is actually not making any value change or something like that. So what is the result of this? So we can take this A inverse first inside the determinant sign. So just like the distribution, so determinant of A inverse into AB, okay, minus A inverse into lambda I, Okay, that is because what I did here is I distributed this A inverse inside of this determinant sign, and we are keeping the right determinant A as it is. So this is equal to 0. Okay, so this is equal to what is A inverse times A? That is I. So IB minus A inverse lambda times determinant of A equal to 0. See, we are actually nearby our solution. So now I am actually going to multiply this determinant A inside this. So this will be I B A minus A inverse A lambda is equal to 0. This is determinant BA minus A inverse A, or A inverse is lambda I, so this is lambda I equal to 0. See, this is equation number 2. What is this? BA minus lambda I equal to 0. BA minus lambda I equal to 0 is the characteristic equation of BA matrix BA. We started from the characteristic equation of matrix AB, and we reached the characteristic equation of matrix BA. So obviously equation 1 and equation 2 are same, and so that the roots lambda 1, lambda 2, lambda 3, etc., lambda n, if n is the order of the matrix, are the roots of both the equation. And we can say that the characteristic roots of AB and BA are the same, and that's the proof. Okay, so I explained from the beginning till this proof because this proof with the explanation of the initial items can give you a clear picture about the characteristic roots and the characteristic equation of a matrix. I hope everyone is really enjoyed this session of the proof and the information. If you really wish to get the informations of this kind and the sessions of the same kind, you please share, like, and subscribe my channel. Don't forget to press the bell icon, and that will give you a chance to get all the videos that I am uploading here in this platform. And thank you very much.